All right, ladies and gentlemen, we're going to go over our plate tectonics notes here. Continental drift hypothesis was first proposed in the early 1900s by Alfred Wegener. His hypothesis was that continents were once joined together in a single large landmass called Pangaea, and that Pangaea eventually split apart and that the continents gradually moved to their present locations. This hypothesis was called the continental drift hypothesis. So the evidence that supported this was that the continents look like they fit together like puzzle pieces. If you look at South America and Africa, their coastlines seem to kind of fit together here. Additionally, there were matching fossil records. Fossils of plants and animals that lived in the same geologic periods were found somehow on completely separate continents with no means for those plants or animals to otherwise spread across those continents. And then number three, there were matching rock layers in South America, Africa, India, Antarctica, and Australia that were incredibly similar. These Wagner showed that the same three rock layers occur in all of those locations. Now, these are from them being deposited all at the same time in a similar place. As a result, here's an example of those rock layers right here. All right. And as a result of these three different pieces of evidence, it's believed that we had at one point some kind of a supercontinent where all of our continents or all of the landmass was more or less grouped together. Now, people were reluctant to support this hypothesis at first. People believed that the evidence was compelling, but wouldn't we feel the movement? Also, wouldn't there be evidence to show that the continents were still moving today? Now, additionally, Wagner was a meteorologist and not a geologist, which kind of lessened his credibility in this field. Now, it wasn't until the 1960s, relatively recently here, that Henry Hess made a discovery that would validate Wagner's hypothesis. He used a new technology called a radar, and he was examining the seafloor with it, and he noticed that both trenches and mid-ocean ridges existed down there. Now, he proposed that the seafloor spreading theory has proposed that hot magma below the Earth's crust rises up towards the surface at mid-ocean ridges, and then as it cools, it moves sideways, pushing the seafloor from the ridge in both directions. So it's spreading apart, and new magma is coming up into that middle and forming new crust or oceanic crust. Now, as the seafloor spreads at a mid-ocean ridge, new seafloor crust is created. The older seafloor moves from the ridge in opposite directions. This helped explain how the crust could move and the why needed to explain Wagner's continental drift. So the evidence for this was in 1968, scientists aboard the research ship, the Glomar Challenger, began gathering information about the rocks on the seafloor, and scientists found that the youngest rocks were located at the mid-ocean ridges, whereas older rocks were located further away. So again, the magma pushes up at the mid-ocean ridge, it makes new crust, those plates slide to the sides, allowing more magma to come up. Now, subduction zones at the edges of these plates, where two different plates meet, or where trenches are where this crust will be destroyed as it gets pulled back into the magma. Now, let's see if the video will play for us here. All right. So what we can see in this image is that the magma's... Oh, it looks like it might want to play for us. Here we go. All right, so what you can see in this little clip here, we're not going to watch the whole thing, but you can see the magma rising up here. When it hits this mid-ocean ridge, it slides off to the side, and this new crust will slide along, as we can see here, this magma acting as a bit of a conveyor belt for it, and then new crust will continue to form. Now, here's what we call that subduction zone. This is where we would have that oceanic trench occurring, and that plate is then being pulled back down into the earth, and it's melting. So it's reforming, and it's going to continue on this convection current here and continue moving through. All right, the theory of plate tectonics. Both Hess's discovery and Wagner's continental drift hypothesis combined into what scientists now call plate tectonic theory. Theory of tectonic plates, or the Earth's lithosphere, the crust, and the part of the upper mantle are broken into plates, which move along the asthenosphere, which acts as a plastic-like layer of the mantle. Here we can see that. So we have the Earth's crust up here, and then our asthenosphere. All right, so the way the plates move, there are a few steps here. First off, it's still debated what the initial driving force of plates are. Plate tectonic theories developed in the 50s and 60s, so it is still a relatively recent theory. The inner core and the outer core of the Earth are extremely hot, and as a result, this thermal energy heats the mantle layer. So this is the heating force right here. Now, this heat is almost infinite. It shows no signs of slowing down. We will have heat there for a very long time. So the mantle heats the magma. The magma rises straight up because it's then less dense as those particles spread out. These areas become the thinnest places on the lithosphere crust. The hotter mantle moves underneath the crust, assisting in the plate's movement like a conveyor belt. So just like we saw in that video there, it's sliding along underneath the crust, causing it to move. As the plate moves away from the mid-ocean ridge, it becomes older, thicker, and more dense. So it starts to thicken up as it moves along, as more magma starts to cool along it. The oldest and densest part of the plate is located in the subduction zones, where it's getting pulled back down into the earth. This is because the plate is more dense, or as the plate becomes more dense, it subducts or sinks below the opposing plate. This forms our trenches. The dense part of the plate subducts into the asthenosphere and mantle, experiencing a substantial amount of heat. As it sinks, it pulls the tectonic plate with it. This is called slab pull. So as it starts to sink down, it's going to pull the rest of that slab, or the continent or the oceanic plate that it's attached to, down with it. So once it starts to go down a little bit, it's going to continue pulling with it. Again, kind of like a conveyor belt. The force of this slab pull is due to gravity. The plate then melts more as it sinks into the Earth's outer core layer. The resistance of its force causing magma to rise above. This can often be the cause of volcanoes along oceanic plates, as well as earthquakes and tsunamis. Eventually, the plate will melt enough that it breaks off from the rest of the plate and just becomes part of that, or it just becomes or melts into magma again. Here again is an image showing this. We see that magma rising up here, and we have that ridge. Let me move my face here. We see that ridge right here pushing the crust along, and then we have that slab pull pulling it down, so it's getting pulled this way constantly, and new gets formed here at the ridge. So the rate of motion. The continents are still moving slowly, and they do so at about the same rate that your fingernails grow. Satellite measurements have confirmed this every year, and each year the Atlantic Ocean gets a few inches wider. Now, we can walk through how things formed. Here's Pangea here. Like I said, it's a mostly connected large land mass. You can see different continents listed on here. And as it breaks up, we then have Gondwana, which is our secondary supercontinent. Here you can still see Africa and South America, as well as Antarctica, India, and Australia, where we were talking about those similar rock layers still attached together. North America is broken off. And we have China, Siberia, Southwest Asia, Tibet, Iran. All right. Things are starting to break up more. We have separate continents now, except for Australia, still attached to Antarctica. And then as we keep going to 14 million years ago, we're starting to look a little bit more normal until we get to the modern world. Now, if we look to the, yeah, all right. Now, as we look to the future, there's a chance that other supercontinents could form or land masses could move back together, but that's going to again be millions of years in the future, because if you look at any of these dates, none of these changes have happened quickly. All of these changes have taken millions of years to occur, because again, the continents are only moving at the same rate that your fingernails grow. All right, ladies and gentlemen, that concludes our notes on plate tectonics. I hope you have a great day.